The Columbia Generating Station sits the furthest from the other United States nuclear power plants, as it is the only plant in the Northwest. Washington State has many power generating sources, but only one nuclear power plant. The Columbia Generating Station is situated 10 miles north of Richland, Washington, at the confluence of the Yakima and Columbia Rivers. The plant was built in 1984 and contributes for 7.8% of the power generated in Washington. The state's generated power comes from 64.6 hydroelectric, 14.4 natural gas, 7.8% nuclear, which is all from Columbia, 2.9% coal, 8.7% wind, and 1.6% biomass, petroleum, and solar power. Nuclear power plants are usually built on the shores of rivers because the water provides cooling by absorbing the heat that is created by the plant. The water for the Columbia Generating Station comes from the Columbia River. While the station draws approximately 20 million gallons of water per day, this has very little impact on the environment because 23 million gallons of water flows downriver every minute. The station also releases water back into the river. The water is not radioactive, thereby replenishing water without dumping radioactive waste. It is specifically located in rural Washington where few people live, minimizing impact and potential cases of failure. The site takes up approximately 1,089 acres of land. In the center is the nuclear reactor where most of the energy comes from. To the bottom are the cooling towers, which condense the water used by the reactor so that it can be reused. To the top is the dry spent fuel storage, since spent fuel is still radioactive and needs to be safely stored. To the top right is the power plant substation, where they pass the generated electricity through to wherever it's needed. Then there's just parking for the employees that the power plant needs to function. Columbia is the successor to the Hanford site, which was decommissioned in 1989 due to safety issues. There are three main consequences to nuclear power plants. 1. The risks that come from using radioactive material. 2. The production of nuclear waste. And 3. Uranium mining. Ionizing radiation can very quickly become lethal to essentially anything living. To counteract this, nuclear power plants are situated far away from major populations. The best way for production is to have several barriers that encase the radioactive material. From the core to the outer layer, it goes. Non-soluble ceramic pellets that encase the nuclear fuel, corrosion-resistant zirconium metal tubes that encase ceramic pellets, reactor coolant, which is water, within a reactor vessel, reactor's vessel with a 6 to 9 inch steel inner wall, the primary containment, which is a concrete shield wall several feet thick surrounding the reactor vessel, and a secondary containment, which is the reactor building's outer wall with negative inside air pressure and high-efficiency filtration systems. There are also numerous safety procedures in place, mechanical and human, in cases of failure or unusual conditions that minimize damage to a significant extent. Workers have regulation protecting them from being exposed to more than 500 milligrams of radiation per year. While radiation exposure can be dangerous long-term, the several protections in place make the dangers minimal. As for nuclear waste, Columbia Generating Station's spent fuel is stored in steel-lined, water-filled concrete pools in massive airtight canisters as well as 45 dry casks. The method is built to contain as much radiation as possible, but as spent fuel accumulates, the risk of having so much radioactive material increases. While there are efforts for a national long-term nuclear waste storage facility, it is yet to progress. Other countries reuse their spent fuel into more fuel, but the United States is yet to do so. Finally, the uranium mining necessary to produce fuel can damage the environment. Uranium mining can be dangerous for miners, and uranium mines can also leak uranium, contaminating the area. Miners and mines have regulation to maximize safety, and things like nuclear fuel reuse and breeder reactors try to reduce uranium demand. Should these efforts be successful, the danger of uranium mining would be low.
The Columbia Generating Station uses a General Electric boiling water reactor Type 5, which works by heating water, converting it to steam, and then using that steam to turn the turbine of an alternator to generate electricity. To generate heat, a boiling water reactor uses the fission of uranium-235 stored in fuel assemblies. When a neutron collides with uranium-235, uranium-236 is formed, which then breaks down into two other particles, releasing thermal energy that has come from nuclear energy. When uranium-236 breaks down, it also releases a few neutrons that go on to break down other uranium-235 atoms, creating a chain reaction and releasing more energy. To heat the water, water is flowed around the fuel assemblies without coming into contact with any radioactive material to absorb the heat released. The energy from nuclear fission is able to excite the water molecules and turn them into steam, which is collected at the top of the boiling water reactor. Afterwards, the steam is directed towards a turbine, causing the turbine to rotate. The turbine is connected to a loop of wire within an electric generator. The electric generator itself has magnets inside of it that create a magnetic field. As the loop rotates within the constant magnetic field, the conditions for electromagnetic induction, a wire experiencing changing magnetic flux, are fulfilled, converting mechanical energy to electric energy. Hence, our electricity is generated and then it flows to wherever it's needed. Now, as for what happens to the generated electricity, it is stepped up, for the most part carried over 500 kilovolt transmission lines, stepped down, and then distributed. According to Chint Global, step-up transformers tend to lose 1 to 2%, so I'll go in the middle and say 1.5%. Looking at the United States Energy Information Administration's map of electricity transmission lines, much of the power can be routed through 500 kilovolt transmission lines, which have a pretty low loss, so that's what I'm going with. It's about 250 miles to Seattle and about 300 miles to Spokane and Portland. Lastly, according to American Electric Power, transmission lines lose about 12.6 megawatts per 100 miles at a 1000 megawatt load, and we end up with this equation. The next equation is the same as the second, just reversed. Again, according to Chint Global, percentage loss to distribution ranges from 4 to 6%, so just going in the middle again, it's 5%. In the end, it turns out that about 90% of Columbia generating stations' energy is received, which is pretty good. Now is a good time to note the EIA's estimation that transmission and distribution losses in Washington are about 3.57%. This doesn't necessarily invalidate the just calculated efficiencies, as there are many possible reasons for the discrepancy. Included but not limited to the fact that the EIA's calculation applies to all energy sources and not just nuclear, as well as the fact that my estimates don't account commercial, industrial, and transportation sector consumption, since I didn't find information for that. Furthermore, I don't know the exact transformer and distribution losses, so that muddies things a bit. In order to generate electricity efficiently, nuclear power plants have to be able to make a lot of steam and then use that steam well. To make a lot of steam, nuclear power plants use a lot of uranium. Since we don't have uranium, we'll just use a hot plate to simulate the energy uranium gives off. To use the steam, they direct the steam towards a lightweight turbine that maximizes the turbine's speed to maximize the energy generated. They also use a steam dryer to prevent water from corroding the parts. Finally, they need fail-safes. Nuclear power plants have control rods that absorb neutrons and halt nuclear fission and hence energy release, and we have a pressure valve to prevent pressure buildup so our beaker doesn't explode. The first iteration of our model was with our initial soda wheel in a regular position. On this graph, it is the middle left column, and we got about 1 millijoule of energy. We then modified our model by changing the type of wheel. The paper wheel is made out of a manila folder, and our second soda wheel is more uniform in construction. Our paper wheel struggled to rotate because our steam was wet, essentially damaging the wheel because it was saturated with water, flimsy and heavy. Our second soda wheel performed much better than our first, as it didn't wobble side to side anymore and more energy could go into rotating the wheel. We calculated about 6 microjoules and 8 millijoules respectively. Our third modification came from us noticing that the support for our wheels was wobbling a lot. We secured it and then took more measurements. In the end, every wheel improved as more energy went into rotating the wheel rather than just moving it around, translating into more electricity generated. The paper wheel, our first soda wheel, and our second soda wheel measured about 2 millijoules, 8 millijoules, and 13 millijoules respectively. Our equation came from rotational kinetic energy equaling 1/2 rotational inertia times angular velocity squared. We set rotational inertia as 1/2 mass times radius squared, and rotational velocity as circumference times rotations per minute divided by 60. And then on the right is our model.